Welcome back to Sleepy Science Nerd, the channel where we explore the universe, one gentle yawn at a time. Tonight, we're setting off on a slow, relaxing journey into one of the biggest questions you can possibly ask. Where does space stop? At first, it sounds like the kind of question a curious kid might ask while staring out the car window at night. But the more you think about it, the more it feels like one of those optical illusions, obvious until you actually try to solve it, and then your brain does a backflip. As always, my goal here is simple: help you unwind, maybe even drift off to sleep, or at least give you a few minutes where your everyday worries shrink down to the size of dust motes as we zoom out, way out past our little blue planet, past the solar system, past galaxies so far away they look like tiny smudges of light. Just one warning, there's a small risk this will get too interesting and keep you awake. If that happens, hey, at least you'll leave with some fresh cosmic trivia for your next coffee break. Before we float away into the stars together, don't forget to like this video and subscribe if you haven't yet. It really helps our cozy little science corner grow. And tell me in the comments, where are you tuning in from and what time is it for you right now? Maybe you're curled up in bed in Helsinki at 11:43 p.m. or sitting in a Melbourne cafe at 3:00 in the afternoon, pretending to work while actually watching videos about galaxies. Either way, I love seeing our little constellation of viewers scattered across the globe. All right, get comfortable. Take a slow breath. You don't need to take notes. Just let the words drift over you like the faint static of the cosmic background radiation. So, what is space exactly? That black backdrop we see when we look up at night. What is it really? Most people think of it as nothing, an endless, empty gap where stars float, planets spin, and maybe the occasional missing sock drifts eternally. But here's the twist: space is not truly empty. In fact, it's one of the most active, mysterious, and surprisingly busy parts of the universe. For centuries, the common view was that space was just a fixed stage, like a theater floor, solid, flat, unchanging, where the actors, planets, stars, comets moved around. This was the way Sir Isaac Newton imagined it. Space was absolute time, ticked the same for everyone, and nothing about that invisible stage ever changed. Then along came Albert Einstein, the man with gravity-defying hair and even more gravity-defying ideas. He tossed Newton's tidy stage set right out the window. According to Einstein, space isn't just sitting there passively. It's a stretchy, bendy fabric that responds to mass and energy. Space and time, he said, are woven together into something called space-time. And space-time can warp, twist, and stretch depending on what's in it. Picture a trampoline. Set a bowling ball in the middle and the surface dips. Now roll a marble across it. Instead of moving straight, the marble curves around the dip. That's a simple way to picture how gravity works, not as an invisible pull, but as objects following the curves in the fabric of spacetime. Massive objects like planets and stars warp spacetime around them. We fall toward Earth not because it's yanking us like a magnet, but because Earth has made a little dent in space-time, and we're sliding toward the center of that dent. All right, you might say, so space bends. But if there's nothing in a region, like the gaps between galaxies, that's just empty, right? Not quite. Even in the most desolate stretches of the cosmos, space is humming with activity. Thanks to quantum mechanics, we know that empty space is anything but empty. At unimaginably tiny scales, far smaller than atoms, space is alive with quantum fields. These fields aren't in space. They are space. Every particle we know comes from its own field, electrons from the electron field, photons from the electromagnetic field, and so on. Even when no particles are present, these fields are never completely still. They jitter and flicker with tiny fleeting particles that appear and vanish almost instantly. This restless motion is called vacuum energy. Think of it like the surface of a calm pond. From a distance, it looks perfectly still, but get close and you'll see ripples, bubbles, maybe even a bug skimming across. The vacuum of space is the same from far away. It looks like nothing but zoom in, and it's teeming with invisible activity. And here's where it gets even wilder. Space itself can expand, not in the sense of objects flying apart through pre-existing emptiness, but in the sense that the very fabric between them stretches, like the squares on graph paper growing larger. This isn't just theory. We see evidence of it everywhere we look. Now I get it. That's a lot to take in. The nothing you thought was nothing turns out to be a bendable, stretchable, shimmering something. But in a strange way, that's comforting. Even in its quietest, darkest corners, the universe is still alive, with a gentle hum, and maybe knowing that you'll never look at empty space quite the same way again. Last time we talked about how space isn't just a boring, empty void. It bends, it hums, it stretches, and apparently, it also refuses to sit still. So now that we know space can expand, let's talk about just how far it actually goes, or at least how far we can see. Picture this. You're standing on a quiet hilltop at night, looking up at a sky so clear, you feel like you could reach out and tap the stars. It feels infinite, right? But here's the truth. There's a limit to what you can see. Not because the universe ends there, but because light simply hasn't had enough time to reach us from beyond a certain distance. This is what astronomers call the observable universe. Think of it as a giant bubble surrounding us, not made of soap, but of information. Inside the bubble, everything we've been able to detect: light radio waves, gravitational waves, cosmic microwave background, basically anything that's had time to travel here since the very beginning. The key word here is observable. It doesn't mean there's nothing beyond. It just means we're not lucky enough to have seen it yet, like standing in a foggy valley and only seeing the trees nearby. The forest could stretch on for miles. You just don't know. Now, here's where it gets weird. You might think the farthest we can possibly see would be about 13.8 billion light years away, since that's roughly the age of the universe. Light travels at, well, the speed of light, right? Shouldn't that be the edge? If only the cosmos played by such tidy rules. Because of the expansion of space itself, that boundary is actually much farther out. Our observable universe currently has a radius of about 46.5 billion light years in every direction, making it nearly 93 billion light years across. Yes, you heard that right. Even though the universe is only 13.8 billion years old, the light from the farthest galaxies we can see started its journey when the universe was young. But the whole time it was traveling, space kept stretching, pulling those galaxies farther and farther away. Here's a visual. Imagine you put raisins in a loaf of bread and stick it in the oven. As the bread bakes, the raisins spread apart. Now picture one raisin sending a hello to another just as the baking begins. By the time that hello arrives, the bread has expanded, so the distance covered is way more than you first imagined. This leads us to something called the cosmic horizon. It's not a wall you can slam into with a spaceship. It's more like a fading of information. Beyond this horizon, light hasn't had time to reach us since the Big Bang. It's like trying to hear a song from a speaker that's just too far away. The sound waves haven't made it yet. And just when you think you've got the hang of it, there's another twist. Some galaxies are moving away from us so fast, thanks to the accelerating expansion of space, that the light they're emitting right now will never reach us. Not in billions, trillions, or quadrillions of years. They're beyond what's called our event horizon, visible now only because of the light they sent long ago, but destined to vanish from view forever. It's a little bittersweet. The night sky we see now is full of stars and galaxies that future humans, if there are any, might never see again. The universe is like a friend waving from a train, platforms slowly fading into the distance until they disappear around the bend. But there's a beautiful side to this too. Every single star, every galaxy, every tiny smudge of light in our night sky is part of our observable bubble. It's ours in a way, not because we own it, but because we can witness it. Roughly 2 trillion galaxies each, with millions to trillions of stars, all sending out ancient light that's been traveling for eons just to reach your eyes, or your telescope lens, or your phone screen as you scroll this video in bed. Here's another fun fact. Everyone, everywhere, has their own observable universe. If you were standing in a galaxy 10 billion light years away, your cosmic bubble would overlap with ours a bit, but also include regions we'll never see. In other words, there's no single master view of the cosmos. Each observer gets their own slice of the grand cosmic cake. And while our observable universe is massive 93 billion light years across, it's almost certainly just a tiny fraction of the whole. What's beyond more galaxies, endless space? Something so strange our physics can't describe it yet. We can only guess. Here's how I like to think of it. Our cosmic bubble isn't a prison. It's a gift. A window into the story of the universe, expanding slowly over time as more light has the chance to arrive. Every day, photons from just a little farther away finally make it here, adding new pixels to the ultimate time-lapse photo. It's a reminder that even if we can't see everything, what we can see is already breathtaking, a glowing record of billions of years written in light. Here on Professor Cozy, we love taking big, mind-bending questions like, where does space stop, and turning them into calm late-night conversations you can drift off to. And one of my favorite space facts to share is this. When you look up at the night sky, you're not just seeing space, you're seeing time. Every star, every glowing smudge of light out there is a kind of time capsule. The farther away something is, the older the light we're seeing. In a very real sense, astronomy is time travel. You don't need a DeLorean or a flux capacitor, just a clear night, a good telescope, and a little patience. Let's start with the basics. A light year is the distance light travels in 1 year, about 6 trillion miles, or nearly 10 trillion kilometers. So if a star is 100 light years away, the light hitting your eyes tonight left that star a century ago. You're seeing it as it was when your great-grandparents were young. Now stretch that idea into the deep reaches of the observable universe. Some of the galaxies we detect are billions of light years away. That means the light we see from them began its journey long before Earth even formed. Before our oceans existed, before the first cell came to life, that light was already racing through space toward a future observer, toward you. Astronomers have a handy term for this look-back time. If a galaxy is 8 billion light years away, its look-back time is 8 billion years. When you gaze at it, You're looking halfway back through the universe's entire history. It's humbling and a little spooky. In some cases, we're looking at galaxies as they were billions of years ago, and they may not even exist anymore. They could have merged with others run out of fuel for star formation or drifted beyond our cosmic horizon, so their new light will never reach us. What we see is a fossil, an echo frozen in time. But light doesn't just carry age, it carries information. And as it travels across the expanding universe, it stretches a phenomenon known as redshift. It's like the pitch of a siren dropping as it moves away from you, except here, it's the wavelength of light getting longer. Almost all distant galaxies are receding from us, so their light is shifted toward the red end of the spectrum. By measuring redshift, astronomers can calculate how far away a galaxy is, how fast it's moving, and even infer details about how big the universe is and how it's changed over billions of years. If you've ever searched, "How big is the universe?" and found yourself in a rabbit hole of numbers and diagrams, well, redshift is one of the main tools behind those answers. And that brings us to one of my favorite relaxing science stories here in Professor Cozy. The idea that telescopes are basically time machines. A backyard telescope might show you the moon as it was just over a second ago, or Jupiter's clouds as they were 40 minutes ago. A giant observatory could show you galaxies from hundreds of millions of years in the past. Then there are the heavyweights, Hubble James Webb, and the next generation of space telescopes. These can peer so far into space, and thus so far into the past, that they capture light from the first galaxies ever formed. We're talking about structures that took shape just a few 100 million years after the Big Bang, which is like flipping back to the first few pages in the universe's storybook. Here's the twist in our quest to understand the universe's future. We spend almost all our time staring into its past. The present is actually the one thing we can never see directly in the cosmos, not in real time. Even the sun you see in the sky is already 8 minutes old by the time its light reaches Earth. That delay is a gift. It lets us piece together a timeline of cosmic history, not just as it is, but as it was at different stages. Look in one direction, and you might see a young galaxy bursting with new stars. Look in another, and you might glimpse ancient light from a time when the first galaxies were just starting to form. The sky becomes a patchwork quilt of different eras, stitched together by photons traveling across unimaginable distances. I like to think of it this way. You and I live inside a museum made entirely of light. Each star, nebula, and galaxy is an exhibit frozen in time, its light finally arriving after an impossibly long journey. You don't have to walk from room to room. The exhibits come to you, crossing billions of years, just to appear in your corner of the observable universe. And the most peaceful part, this isn't some rare event. This is what happens every time you look up. Whether you're an astronomer in an observatory or just someone standing in their backyard with a cup of tea, you're looking into the past, catching whispers from billions of years ago. So next time you step outside on a clear night, remember, the stars aren't just twinkling, they're speaking quietly across time. And Professor Cozy will be right here to help translate those whispers into stories you can fall asleep to. We've talked about how looking at the night sky is like looking into the past, each pinpoint of light, a messenger from another time. But if you keep looking farther and farther, there's a limit to how far those messengers can reach us. Astronomers call that limit the cosmic horizon. It isn't a wall. There's no invisible barrier out there stopping light from coming in. It's simply the farthest distance from which light has had time to reach us since the universe began. Because the universe is about 13.8 billion years old and has been expanding the entire time that Edge is now about 46.5 billion light years away in every direction. The easiest way to imagine it is like standing on a ship in the middle of a calm ocean. Wherever you turn, water stretches out to the horizon. You know the ocean continues beyond that hazy line, but you can't see it from where you are. The cosmic horizon works the same way we know the universe goes on past what we can observe, but light from those regions simply hasn't arrived yet. And here's something even stranger. The horizon is always moving. Every day, light from slightly farther away finally reaches us, so our view slowly expands. But at the same time, the expansion of space is accelerating, and some galaxies are being carried away from us so quickly that any new light they emit will never catch up. They're already slipping beyond reach, visible to us now, only because of the ancient light they sent long ago. That means the night sky is changing, even if we can't notice it in a single lifetime. Some of the galaxies we see today will eventually fade from view, not because they've vanished, but because the space between us has stretched too much for their light to bridge the gap. It's a strange balance, the horizon giving us more to see over time, while also quietly stealing things away. And just as every person has their own unique path through life, every point in the universe has its own horizon. If you are standing on a distant galaxy, your cosmic view would overlap ours in some places, but also include regions we'll never see from here. We often imagine an edge as something solid, a cliff, a wall, a finish line. But the cosmic horizon is softer than that. It's a boundary set by time and the speed of light, not by any physical structure. And in a way, it makes the universe feel more alive. Every photon that arrives from just inside that horizon is like a new page in a story that's been unfolding for billions of years. What lies beyond? We can guess, we can run simulations, we can build models, but until that light reaches us, if it ever does, it will remain part of the universe's secret chapters. And maybe that's not such a bad thing. Stories are often better when they don't give everything away all at once. If the cosmic horizon is the edge of what we can see, then the expansion of the universe is the reason that edge exists in the first place. The truth is, the universe just won't sit still. This idea was a shock to scientists a century ago. Back then, many thought the cosmos was static stars and galaxies fixed in place, eternal and unchanging on the largest scales. But then Edwin Hubble came along with his telescope and discovered something surprising. Almost every galaxy he looked at was moving away from us. Not only that, the farther away a galaxy was, the faster it seemed to be receding. At first glance, it might sound like we're in the center of some grand cosmic explosion with everything flying away from us. But it's not that galaxies are rushing through space like cars on a highway. It's that space itself is stretching, carrying the galaxies along with it. The best analogy is still the raisin bread. Picture dough full of raisins. As the dough rises, every raisin sees every other raisin moving away, not because the raisins themselves are moving much, but because the dough between them is expanding. No raisin is the center. No raisin is special. From anywhere in the loaf, the view looks the same. Everything else is drifting away. This expansion means that the distances between unbound galaxies, those not held together by gravity, are growing all the time. Our Milky Way isn't expanding because its stars are bound tightly by gravity. neither is our local group of galaxies. But over larger distances, the stretch of space becomes impossible to ignore. For a long time, scientists assumed that gravity would eventually slow this expansion. After all, with enough matter pulling inward, maybe the universe would stop stretching and even begin to contract, collapsing in on itself in a big crunch. But in the late 1990s, observations of distant supernovae revealed something even stranger. The expansion isn't slowing down, it's speeding up. Something we still don't know exactly what is pushing the universe apart faster and faster. We call it dark energy, not because it's spooky, but because it's mysterious. We don't know what it's made of, where it comes from, or why it behaves the way it does. All we know is that it now dominates the universe, outpacing the pull of gravity on the largest scales. This acceleration has consequences. More and more galaxies are drifting beyond our cosmic horizon, slipping out of reach forever. In the unimaginably distant future, observers in our galaxy might see only the faint glow of a few nearby galaxies, with the rest of the universe's light erased from view by the relentless stretching of space. It's a little melancholy, but also a reminder that we live in a special moment, a time when we can still see and study billions of galaxies. The universe is open to us now, in a way it won't always be. And yet, there's something strangely comforting in knowing that the expansion will continue quietly for billions of years. It's not a violent tearing, it's a gentle drift, like clouds moving apart in a wide sky. The universe began close and dense, like an orchestra tuning before the music starts. Over time, it expanded, cooled, and formed the cosmic structures we see today. And now it's still growing, the song still playing, but changing slowly, almost imperceptibly, over the span of human lifetimes. From here on Earth, it's easy to forget we're part of that motion. But every heartbeat you've ever had, every breath you've ever taken, has happened on a little world drifting in the middle of that cosmic stretch. And whether or not we ever understand the full nature of dark energy, the fact remains the stage we're on is getting bigger all the time. When people hear that the universe is expanding, the first question is almost always the same. Expanding into what? It's a fair question. After all, we're used to balloons swelling into the air around them, or soap bubbles pushing against the space outside. But the universe doesn't work that way. It doesn't need an outside to grow into. Space itself is all there is. When it stretches, it's simply increasing the distance between points within itself. Still, the idea of shape is important because it's like knowing the layout of the stage before the play begins. If you want to understand the universe's past and future, you need to know the geometry it's playing out on. Scientists generally talk about 3 possible shapes close like the surface of a sphere. In this kind of universe, if you kept going in a straight line long enough, you could theoretically end up back where you started. It's cosmic déjà vu, open-shaped like a saddle, with space curving outward. It goes on forever, but in a way that subtly changes how gravity behaves across enormous distances, flat, neither curved inward nor outward, like an endless sheet that just keeps going. Figuring out which one we live in is no small task. You can't exactly fly a spaceship to the edge and look back. Instead, scientists use light as their ruler. By studying how light from distant galaxies bends, and by examining the faint afterglow of the Big Bang, the cosmic microwave background, they can measure the curvature of space itself. The verdict so far, the universe appears to be remarkably flat. Not perfectly flat. Our measurements have limits, but so close that any curvature would only become obvious far, far beyond the regions we can currently see. Now, flat doesn't mean boring. In fact, on the largest scales, the universe has a structure that's surprisingly beautiful. Matter isn't spread evenly. It's gathered into vast webs and filaments, with galaxies strung along like pearls. These filaments meet at enormous clusters, and between them are gigantic voids, stretches of space so empty you could travel millions of light years without hitting a single star. From far away, it looks like an intricate network, glowing threads, and dark gaps woven together by gravity over billions of years. And here's the fun part. No matter where you stand in that web, the view looks roughly the same. There's no cosmic center, no special front row. Everyone gets the same general experience, except maybe you're looking at a slightly different set of galaxies than someone on the opposite side of the cosmos. Thinking about the universe's shape can feel abstract, but it's also strangely personal. You and I, every atom in our bodies, are part of this grand geometry. The carbon in your cells, the oxygen in your lungs, the calcium in your bones. All of it was forged in stars scattered across that cosmic web. And those stars, they were shaped by the very curvature and expansion of space we're talking about. So in a way, you're not just living in the universe. You are the universe, a tiny piece of its shape made self-aware, wondering what it's made of. And that if nothing else is worth a smile before bed, and if the idea of a closed universe makes you nervous, like we might suddenly bump into ourselves, don't worry. Even if space were curved back on itself, the distances are so immense that you'd have to travel billions of years at the speed of light just to complete one loop. That's way more road trip snacks than anyone could carry. But maybe that's the point. The universe's shape isn't there for us to conquer like a map in a video game. It's there to hold the story, all of it. The galaxies forming stars, burning out planets, spinning quietly in the dark, and us lying here thinking about it all. So tonight, if you find yourself staring up at the ceiling before sleep, try this. Instead of counting sheep, picture the cosmic web. Let your mind drift along its glowing threads, across galaxies and clusters through the vast empty voids, until the patterns fade into the quiet. Somewhere in that endless shape, you're just one small point. But without you, it wouldn't be quite the same picture. If the shape of the universe is the stage, then time is the lighting. It doesn't just shine evenly everywhere it bends, stretches, and plays tricks, depending on where you are and how you move. And unlike most tricks, this one is backed by Einstein. We grow up thinking of time as a constant drumbeat. 1 second here equals 1 second everywhere else. But in the universe, that's not quite true. Time can speed up or slow down depending on gravity and velocity. This isn't science fiction. It's been measured, tested, and even experienced by astronauts and satellites. Let's start with gravity. The stronger the gravity you're in, the slower time moves for you compared to someone farther away from that gravity. Imagine you're standing near the surface of a neutron star, one of the densest objects in the universe. If you hung out there for a few hours, ignoring the whole being crushed instantly, problem you'd return to Earth to find that far more time had passed for everyone else than for you. Your friends might have aged years, while you barely ticked forward. It's called gravitational time dilation, and while the neutron star example is extreme, it's happening all the time, even here on Earth. In fact, time at sea level runs just a tiny bit slower than time on top of a mountain. Because Earth's gravity is slightly weaker the farther you are from its center. Your head is technically aging faster than your feet right now, which is a great excuse to say you're young at heart. Then there's velocity. The faster you move, the slower your clock runs, compared to someone who's standing still. This is special relativistic time dilation, the one that makes science fiction writers giddy. If you flew near the speed of light to a distant star and came back, you might have aged only a few years, while decades passed on Earth. It's the ultimate "I missed the reunion" excuse. Of course, we don't notice these effects in everyday life. The differences are measured in nanoseconds, unless you're traveling at incredible speeds or sitting on something with extreme gravity. But for things like GPS satellites, these effects matter. Without correcting for time dilation, GPS signals would drift by kilometers each day, which means your phone could tell you you're in the next city over while you're still in your kitchen. Here's the thing. Once you understand time this way, the idea of a universal now starts to fall apart. There's no single master clock in the universe. What's now for you might be in someone else's future or past, depending on where they are and how they're moving. The universe doesn't tick together like a metronome. It flows more like a vast winding river with eddies, slow stretches, and rapids. And that brings us to one of my favorite mind-bending thoughts. When we look at distant galaxies, we're not just looking at faraway places, we're looking into different times. A galaxy 10 million light years away appears to us as it was 10 million years ago. The Andromeda Galaxy, the closest spiral neighbor to our Milky Way, shows us a snapshot from 2.5 million years ago, long before humans existed. If aliens are looking at Earth from there right now, they're seeing our planet in the middle of the Ice Age. This look-back time means that the farther out we see, the earlier in the universe's story we're reading. The cosmic microwave background, the faint glow from the Big Bang, is the earliest chapter we can see directly, a baby picture of the universe when it was just 380,000 years old. Beyond that, the light hasn't had time to reach us yet. Here's where the cosmic prankster part comes in. Because space is expanding, that ancient light we see from the early universe is stretched, its wavelengths elongated into the microwave range. This redshift means that the universe's history isn't just playing back for us. It's been distorted and slowed down by the very fabric of space. Imagine watching your baby photos through a funhouse mirror that's slowly stretching apart. It's strange to think of time as something elastic, but that's exactly how the universe treats it. And it's not just a curiosity for physicists. It shapes how the cosmos evolves. The expansion of space, the pull of gravity, the speed of light, they all interact through time to decide what we can see, what we can reach, and what will forever remain beyond our grasp. Even stranger, there's no rule that says time has to move forward everywhere. According to the equations, if you could travel faster than light, which we don't know how to do, you could in theory go backward in time. Of course, faster than light travel comes with paradoxes. Save your grandparents from meeting, and you might
erase yourself from existence. Or worse, you might still exist, but now you're your own uncle. Physics does not recommend this, but maybe the most humbling part of all this is that our personal experience of time birthdays, seasons, the ticking of clocks is just one tiny local version of what time can be. Out there in the wider universe, time is flexible, subjective, and sometimes downright mischievous. So the next time you feel like there's never enough time in the day, remember somewhere out there, time is moving slower. Somewhere else, it's moving faster. And here we are in our own little patch of space-time, just trying to make the most of it, before the next second, however long that lasts, slips away.
And if nothing else, at least, now you have a good line for being late. Sorry, time moves differently. Where I'm from, by now we've talked about the shape of the universe, how it expands, and how time itself bends and stretches. But there's one more piece to this cosmic puzzle, the ultimate boundary on what we can ever know. It's called the cosmic horizon, and it's not just far away. It's the farthest anything can be and still have a chance of affecting us. Think of it like standing on a beach. The ocean seems to go on forever, but there's a line where the water meets the sky, the horizon. You can sail toward it all you want, but as you move forward, the horizon moves too. You never actually reach it. The cosmic horizon works the same way, except it's not water curving away from you. It's space itself, stretching so fast that light from beyond that point will never catch up. That's right. There are places in the universe we will never see, no matter how long we wait or how powerful our telescopes become. They are moving away from us faster than light because of the expansion of space. It's not that they're breaking the cosmic speed limit. Nothing can move through space faster than light, but space itself is expanding, carrying them beyond reach. This means the observable universe, everything we can detect, is only a slice of the whole thing. A very, very big slice, about 93 billion light years across, but still just a portion. Beyond that, we don't know. There could be trillions of galaxies, or there could be something so strange that our physics wouldn't even have the words for it yet. Here's the tricky part. The observable universe isn't the same as the actual universe. The actual universe could be much bigger, maybe infinite. If it is infinite, then there are patches of space so far away that light from them will never ever reach us. They might as well be in a completely separate reality, because for all practical purposes, they are. In a way, this feels unfair. We're curious creatures. We want to know everything, but the universe has drawn a curtain, and no matter how hard we tug, it won't budge. And honestly, maybe that's a good thing. If the curtain ever did pull back all the way, what would we do with all that information? Probably argue about it on the internet. And there's another twist. Because space is expanding faster and faster, thanks to dark energy, the cosmic horizon is actually shrinking in a strange way. Not physically getting smaller, the distances are still huge, but fewer and fewer galaxies will remain visible to us in the future. It's like the lights of a city fading in the rearview mirror as you drive away until only a few remain. Billions of years from now, whoever's left in our galaxy might see only the stars of the Milky Way and its close neighbors. Everything else will have slipped beyond the horizon, taking their light with them. For them, the night sky will be darker, emptier, and unless they have a really good historical record, they might never know there was once a vast universe full of galaxies all around them. It's a little sobering. Right now, we live in a special time when the cosmic stage is still lit up with distant galaxies. We can map the cosmic web, measure the expansion study, the afterglow of the Big Bang. A few billion years from now, that window will have closed. The data will be gone, erased, not by time itself, but by the unrelenting stretching of space. And that's why, in a way, astronomy is a race against time. Not because the stars are going anywhere fast, most will still be here for billions of years, but because the view is disappearing. We're trying to capture as much as we can before the curtain falls on the grandest show in existence. Still, there's something strangely comforting about having limits. The cosmic horizon reminds us that the universe is bigger than our ambitions, and that's probably a good thing. If we could see and know everything, maybe the mystery would vanish, and mystery is half the fun. So here's how I think of it. The horizon isn't a wall. It's a reminder that there's more out there waiting, even if we can't ever reach it. Like a story with a few pages missing, it leaves space for imagination. Maybe beyond that line, there are more galaxies, more stars, more planets. Maybe there are regions where the laws of physics are slightly different, where light dances in ways we can't imagine. Or maybe it's just more of the same. And honestly, either answer is beautiful in its own way. When you step outside tonight and look up, remember the stars you see are all within our cosmic neighborhood, and every single one of them is part of the small fraction of the universe we can touch with light. The rest, well, maybe it's better left as a mystery. It gives us something to wonder about, and wondering is what humans do best. And if you ever feel small thinking about it, try this. Take a breath. Feel your chest rise and fall. That breath is yours. The horizon might keep some things out of reach, but your world, the one you can touch, hear and see, is still full of things you can explore. And in a universe this big, that's more than enough to keep life interesting. We've been talking about the universe as though it's a stage, with its shape, its lighting, and the curtain of the cosmic horizon. But every stage has an ending, and the universe is no exception. The question is, what kind of ending are we headed for? Cosmologists have come up with a few main scenarios, and they range from peaceful fade out to catastrophic grand finale. Let's start with the gentlest one, the heat death. Despite the dramatic name, heat death isn't about fire or explosions. It's about running out of usable energy. In this version of the story, the universe keeps expanding forever. Stars burn out one by one, galaxies drift apart, and everything cools down to near absolute zero. No new stars form, no new light shines. The universe doesn't so much die as it falls asleep permanently. It sounds depressing, but it's also kind of serene. Imagine the cosmos as a bustling city that slowly grows quieter over trillions of years until it's just the faint hum of particles drifting in the dark. No drama, no sudden destruction, just a gentle fading into stillness. Then there's the more dramatic option, the big crunch. This happens if gravity eventually overcomes dark energy, stopping the expansion and reversing it. Galaxies would start to move closer together, then faster, until the entire universe collapses back into an incredibly dense state, maybe even into a singularity, like a reverse Big Bang. Some scientists think this might trigger a new Big Bang, starting the cycle all over again. If that's true, it would mean the universe has been endlessly expanding and contracting forever, like a cosmic lung, breathing in and out, romantic, right? Well, except for the part where everything you've ever known gets crushed into a subatomic speck. And then there's the wild card, the Big Rip. This one's all about dark energy, the mysterious force driving the universe's accelerated expansion. If dark energy's strength increases over time, it could eventually tear apart galaxies, then solar systems, then planets, then atoms themselves. Not to sound alarmist, but in the Big Rip scenario, Even the fabric of space gets shredded. On the plus side, it's the most metal name for an apocalypse ever. Right now, our best measurements suggest that the heat death scenario is the most likely. The universe will keep expanding, and over incomprehensible stretches of time, everything will fade away. But most likely doesn't mean certain. Physics still has unanswered questions, especially about dark energy, and those answers could completely change the forecast. And here's where it gets personal. Even though we're talking about endings trillions of years in the future, thinking about them changes how we see today. When you know the stage won't be here forever, every moment on it feels more precious. There's also a weird comfort in the idea that the universe has its own timeline. We tend to think of our problems as massive and urgent, but compared to the fate of the cosmos, they're, well, small. The universe isn't in a hurry. Even in the most catastrophic scenarios, we've got billions of years before anything big changes. That's enough time to finally finish your reading list. The other comforting thought, we're part of the story now. Stars are still forming, galaxies are still glowing, and life, at least on this tiny blue planet, is still buzzing. The now we're living in is one of the most dynamic, colorful chapters the universe has ever had. If you want to feel truly humbled, think about this. If the universe does end in heat death, then right now might be one of the rare moments in all of time when the cosmos is actually interesting. We have stars to look at, planets to explore, and mysteries to solve. Trillions of years from now, there will be no stargazers, no telescopes, no one to wonder, just silence. So while it's fun to imagine the ending, it's even better to appreciate the middle, because that's where we are. The lights are still on, the orchestra's still playing, and even though the curtain will fall someday, there's no reason not to enjoy the show while it lasts. And if you're still feeling uneasy about the idea of cosmic endings, here's a trick picture. The universe as a giant camping trip. You know it's not forever, but that's what makes the campfire warmer, the stories better, and the marshmallows sweeter. When it's time to pack up, you'll still be glad you were there. So tonight, when you step outside and look up, remember the universe may have an ending, but right now it's still telling its story, and you're in it. Last time we drifted through endings, the quiet fade of heat death, the dramatic lurch of a big crunch, the wild tearing of a big rip, big feelings, big futures. Tonight, let's slow down and sharpen one puzzling piece of that story. How in a universe with a hard speed limit, can entire galaxies seem to slip away faster than light? Isn't that illegal? Not quite. The universe is sneaky, but it's not breaking its own rules. The speed limit, the one Einstein posted in bold letters, applies to things moving through space. But space itself, space gets to do what space wants. And sometimes what it wants is to stretch so quickly that the distance between us and very faraway galaxies grows faster than any beam of light can hope to cross. Think of it like standing on a treadmill that keeps cranking up the speed. You try to walk toward a friend on the other side, but the belt is sliding backward faster and faster. You're obeying the rules. You're not teleporting. You're not sprinting faster than light, but the ground beneath you is conspiring to keep that hug forever out of reach. In cosmology, light is, the walker space is the treadmill, and somewhere a cosmic gym manager is nodding with grim satisfaction. Here's the calmer picture. Galaxies aren't rockets blasting away into a pre-existing emptiness. They're raisins in rising dough. As the dough swells, the raisins separate, None of the raisins has to wiggle. The distances just grow because the dough, the fabric of space, is expanding between them. To a raisin, it looks like other raisins are receding. To the baker, it's simply the loaf doing its thing. This is why astronomers can honestly say that galaxy is receding from us faster than light without setting off sirens. The galaxy isn't zooming through space at superluminal speed. The space between us is stretching so quickly that the separation grows faster than light can close it. Einstein's speed limit is fine. The road is what's moving. If you want a different metaphor, picture a canoe paddling upstream. On a calm river, steady strokes get you forward progress. But in a flash flood, the water rushes past faster than you can paddle. You're moving through the water just fine, but the river itself is dragging you the other way. Swap water for space-time and canoe for photon, and you've got the gist. This isn't just a cute story we tell to help you fall asleep, though if it's helping, you're welcome. We see the fingerprints of this stretching everywhere. Light from distant galaxies gets red-shifted, its wavelength stretched on the journey like a rubber band pulled taut. The greater the stretch, the greater the redshift. Measure that stretch carefully, and you can reconstruct how the universe has been expanding over billions of years, a kind of cardiogram for the cosmos. There's an even more outrageous chapter, cosmic inflation. For a tiny fraction of a second after the Big Bang, the universe didn't just expand, it inflated at a staggering rate, doubling and doubling again, like a rumor at a high school lunch table. In that blink, far shorter than any blink regions of space, leapt apart faster than light could ever hope to connect them. Was the law broken? Nope. Same loophole, same principle. Nothing outran light through space. Space itself ballooned. Inflation helps explain a few otherwise baffling facts. Why does the universe look so uniform in every direction, like a neatly frosted cake, when widely separated regions shouldn't have had time to agree on a temperature? Because they were once close, whisper close, before inflation flung them apart. Inflation smoothed wrinkles, stretched quantum jitters into the seeds of galaxies, and set the stage for everything that came after stars, planets, coffee, and this channel with a suspiciously relaxed narrator. Now back to the here and now, cosmically speaking. Even today, expansion means some galaxies are effectively lost to us. We can see many of them not as they are, but as they were, because their older light left long ago and is only now arriving. But the new light those galaxies emit today will never reach us. The treadmill's too fast. Their tail lights curve around a distant corner. The glow lingers, but the car is already gone. There is a tender sadness baked into that fact. The sky you and I can study is in part a farewell montage. Photons that began their trip before our species learned to tame fire are now just reaching us, telling stories from a past we'll never update. It's like getting postcards from a friend who moved to a town the road no longer reaches. You can hold the postcards, you can treasure them, you just can't visit. And yet there's comfort here too. The slice we can see is staggeringly rich billions of galaxies, each draped in the light of countless stars, each harboring worlds beyond counting. We have enough postcards to wallpaper a cathedral. More arrive every day, slipping under the door with new smudges of history. If meaning depends on what's reachable, then the universe gives us more than we could ever finish reading. Let's take a slow breath and follow one photon. It lifts off from a newborn star in a distant galaxy, brushing past clusters skirting the curved valleys carved in space-time by mass stretched longer and redder with every megaparsec. It crosses voids where almost nothing happens for millions of years at a time. At last, it threads our atmosphere, glances off your cornea, tickles your retina, and fires a neuron that says, "Oh, a star. 14 billion years to become a moment." If that isn't poetry, I don't know what is. So you might ask, could we ever cheat? Could we fold space surf expansion or hitch a ride on the treadmill? The equations offer exotic what-ifs, wormholes, warp drives, engineered bubbles of space-time. They're not entirely fantasy, but they are very allergic to reality as we currently understand it. Negative energy, impossible materials, paradoxes that would make your grandfather uninvite himself to his own wedding. For now, they're thought experiments, lovely ones, theoretical lullabies. And anyway, I'm not sure cheating is the point. The horizon, the boundary, where space outruns light, gives our cosmic story its edges and shadows. Painters need contrast. Musicians need silence between notes. We need the not quite knowable to frame the little patch that is knowable. Mystery isn't a bug. It's the part that keeps us looking up. There's another twist that always makes me smile from any galaxy's point of view. They are the ones at the center of an expanding vista. Not because they're special, but because that's how uniform expansion looks from everywhere. It's a universe of protagonists, each location, the middle of its own observable sphere, each sphere different, each true. If that doesn't humble you and embolden you at the same time, check your pulse. So where does this leave us here on this small, hospitable rock? With our telescopes and our questions and our slightly over-caffeinated curiosity, it leaves us in the sweet spot. We live in an era when the sky is still crowded with evidence, the glow from the universe's childhood, the skeleton of its large-scale web, the spectral lines that betray its chemistry and motion. Future beings, if any, may see less. Earlier beings, if any, saw less. We're at a balcony with the lights still up. If the thought of unreachable places makes you feel small, try flipping it the fact that anything at all is reachable, that the river of night carries so many messages to our shores, is astonishing. You are alive at the same time as ancient light, arriving, able to catch it with glass and mirrors and silicon, able to turn it into pictures and numbers, and if you're very lucky, understanding. That seems like winning the cosmic lottery. Let's end with a gentle image to take to sleep. Picture the universe as a vast, dark sea. Around you, bobbing on the swells, are lanterns, galaxies, each sending a thin golden thread of light across the water. Some threads reach your hands. Some have been cut by the waves. Some were tied so long ago, they're only now touching your fingers. You don't need to grasp every thread. You couldn't if you tried. It's enough to feel a few of them, enough to know there are countless more humming just beyond the mist. And if tomorrow night someone asks whether anything can really move faster than light, you can smile and say, nothing through space. But space has long legs. If you've been following along since last time, we've already seen how the universe might end with a quiet fade into cold darkness, a dramatic collapse, or a catastrophic tearing apart. But here's something that makes all of those endings even stranger. There are parts of the universe we'll never reach, not because they're hidden behind a wall or guarded by cosmic bouncers, but because space itself is stretching faster than light can travel. At first glance, that sounds illegal. Didn't Einstein make it very clear that nothing can move faster than light? Well, yes, but the fine print says that rule only applies to things moving through space, not to space itself. And the universe, clever thing that it is, has been exploiting that loophole since the very beginning. Imagine standing on a treadmill that starts out slow but speeds up over time. Your friend is on the other end, waving at you. You walk toward them at the maximum allowed speed, the cosmic speed limit, but the belt keeps rolling backward faster and faster. Eventually, no matter how hard you try, the distance between you grows. You're not breaking any rules. The treadmill is, or rather, the treadmill just is. It's the universe's way of saying, nice try, but I'm in charge of the floor. A galaxy receding from us, faster than light, isn't like a rocket blasting away into pre-existing empty space. It's more like a raisin in a loaf of bread. As the dough rises, as the loaf swells, the raisins get farther apart without ever moving on their own. None of the raisins or galaxies has to go anywhere. The space between them simply grows. That's the trick. And it's perfectly legal in the cosmic rulebook. Here's another way to picture it: a canoe paddling upstream. On a calm day, your paddling makes progress. But in a flood, the river's current outpaces you. You're still moving through the water the same way, but the water itself is carrying you backward. In cosmology, the river is space and the canoe is light. And right now, in the most distant reaches of the universe, the current wins. We can actually see this in action. Light from faraway galaxies is redshifted, meaning its wavelength is stretched as it travels through expanding space like a rubber band being pulled. The farther away the galaxy, the greater the redshift. By carefully measuring this stretching, astronomers can reconstruct the history of the universe's expansion, like reading tree rings in reverse. But this isn't just a modern quirk. Right after the Big Bang, there was a phase called cosmic inflation, where space expanded so outrageously fast that regions that were once close enough to exchange light suddenly became forever unreachable. This all happened in a fraction of a second, much faster than you could blink, and yet it shaped everything we see today. Inflation smoothed out the lumps in the early universe, stretched tiny quantum ripples into the seeds of galaxies, and gave us the remarkably uniform cosmic background radiation we still detect. Think about that for a second. Some of the light reaching our telescopes today began its journey before the Earth even existed. It crossed gulfs of nothingness for billions of years, only to finally arrive here, where it hits your retina or a camera sensor. Meanwhile, any new light from those same galaxies today will never make it to us. Space is expanding too fast. They're slipping away beyond our cosmic horizon. There's something bittersweet in that. We're looking at a farewell image, a frozen postcard from the past. The galaxy in that picture might not even look the same anymore. It might have merged with another, or its stars may have shifted into entirely new patterns. We'll never see the update. The connection has been cut not by choice, but by the unstoppable swell of space itself. And yet that's also part of the beauty. We're living in an age when the sky is still rich with these cosmic postcards. Earlier in the universe's history, there were fewer galaxies, less structure, fewer stories written in light. Far in the future, the sky might be emptier. Our moment in cosmic history is a sweet spot, just far enough along for the universe to have built a masterpiece, but not so far that it's all faded into darkness. Now you might be wondering, could we ever cheat? Could we build something? A warp drive, a wormhole that lets us skip over space instead of traveling through it. In theory, the equations allow for such exotic shortcuts. In practice, well, those equations also require things like negative energy, exotic matter, and the kind of engineering budget that makes even alien accountants sweat. So for now, they remain beautiful thought experiments, bedtime stories for physicists. There's another curious twist here. No matter where you are in the universe, it looks like you're at the center of the expansion. From Earth, we see all galaxies moving away from us. But from a distant galaxy's perspective, we are the ones moving away. This isn't arrogance, it's geometry. Expansion happens everywhere at once, so every point can claim to be the center of its observable universe, which means, in a sense, the cosmos is filled with billions of main characters, each the hero of their own view. All of this makes our current chapter feel precious, because even if we can't reach those faraway places, we can still see them now. We can still measure their light, read their histories, and let them shape our understanding of everything. The very fact that we can even have this conversation is a privilege of timing. So the next time you step outside at night, take a moment to think about the light hitting your eyes. Some of it may have traveled for millions or even billions of years, dodging dust clouds curving around galaxies and stretching across expanding space just to end its journey with you looking up and thinking, wow, that's not just stargazing, that's catching a messenger from deep time. And as we keep moving forward in this long cosmic story, the horizon will keep changing. Some lights will fade, some will arrive for the first and last time. The treadmill of space will carry some things out of reach forever, but that's okay. Part of living in a universe like ours is knowing that some chapters are meant to be read only once, which means that right now, with the lights still on and the sky still busy, this here is one of the rare moments in all of time when the cosmos is alive with stories, and you and I, we get to be here to hear them. So here's where we are. We've been drifting outward with our expanding universe, watching some galaxies slip over the horizon, not because they moved faster than light, but because space itself is doing the heavy lifting. And if that idea feels slippery, like trying to hold onto soap in the shower, buckle up. It's about to get slipperier. We need to talk about the cosmic event horizon. It's not a literal wall, and there's no sign saying do not cross. It's simply the boundary beyond which light will never reach us, no matter how long we wait. This isn't because light gets tired, it doesn't, or because we've put up some kind of invisible fence, we haven't. It's because the space between us and that light's source is expanding too fast for the photons to close the gap. If you're picturing a sci-fi force field, that's not quite right. It's more like being in a boat in the middle of a river that's widening faster than you can row. You might see a fisherman on the far bank waving at you, but no matter how hard you paddle, the river grows faster than your oars can handle. The fisherman isn't getting farther away by moving. The river is doing all the work. This horizon is a moving target. As time goes on, more galaxies cross it. That means the observable universe isn't just a fixed bubble. It's a bubble that changes over time, and not in a fun birthday balloon way, but in a your favorite stores keep closing kind of way. Here's the strange part. We can still see galaxies that are already beyond this horizon. Remember, the light we're seeing left them millions or billions of years ago when they were much closer. But the light they send out today will never reach us. It's like looking at a friend in a rear view mirror. You're still seeing them, but they're driving away on a one-way street. In fact, about 94% of the galaxies we can currently observe are already permanently out of reach. The light we're catching from them is old news, gorgeous, sparkling, old news, but still news from the past. If you think about it too long, it's a little like realizing that most of the people in a group photo you're looking at have already moved to a different city and never sent you their new address. This leads us to an oddly human question: if we can never go there, and if the present-day reality of those galaxies is forever hidden from us, do they still exist in any meaningful way to us? The physicists' answer is yes, they exist just fine doing whatever galaxies do, but they are no longer part of our causal universe. That's a fancy way of saying we can't affect them and they can't affect us. Our stories have split. It's a bit like living in the same city as someone, then one day the city gets cut in half by an ever-widening canyon. You can wave at each other from the edge for a while, but eventually you're just two specks out of sight. Now here's a twist. The size of our observable universe today is about 46 billion light years in every direction, even though the universe itself is only 13.8 billion years old. How's that possible? That's the expansion of space flexing its muscles again. While light was traveling toward us, the space it crossed was also stretching, so the actual distance to the place that emitted it is much greater now. It's like someone walking toward you on an airport moving walkway, except the walkway is going the wrong way, and the terminal keeps getting rebuilt farther away while you're not looking. This also means the observable universe is not the same as the whole universe. In fact, it's probably just a tiny patch of a much larger, possibly infinite whole. It's like living in a cozy cabin with a big picture window. You can see the mountains, the lake, and the trees, but that's not all there is. There are other valleys, other forests, other oceans. You just don't have a window facing them. And here's where the mind-stretching kicks in there. Could be regions of space where the laws of physics look a little different. Maybe particles behave oddly, or the constants we take for granted, like the speed of light or the strength of gravity, have slightly different values. We'll never know for sure because they're beyond our horizon, which to me is kind of comforting. It's like the universe is saving a few surprises for itself. All of this talk about horizons might sound a little gloomy, like we're slowly losing touch with the rest of the cosmos, and in a way we are, but there's also something freeing about it. The fact that there's a limit doesn't make the universe smaller. It makes the part we can explore feel more precious. It's the same reason a photograph feels special. It captures a moment you know you can't revisit. Of course, if you're feeling adventurous, there are speculative ideas about getting around this horizon problem. Wormholes, warp drives, cosmic shortcuts, the usual suspects. The math sometimes says, maybe, but reality usually says, good luck finding the exotic matter you'd need. Think of it as having the blueprints for a jetpack that runs on unicorn tears. Beautiful to imagine, but you're not flying anytime soon. Still, the horizon isn't a brick wall. It's a moving line, drawn by the interplay of light speed and expansion. And that interplay tells us something profound. The universe isn't just a static backdrop with stuff moving around in it. The stage itself is a live dynamic, and sometimes it steals the show. So, what does this mean for us standing here on our little planet, sipping tea and watching photons that have traveled for eons? It means we're part of a fleeting but extraordinary era. one where the night sky is still rich with the light of faraway galaxies, where we can still map the large-scale structure of the cosmos, and where we can still dream about what lies beyond the edge. One day, far in the future, our descendants might look up and see only the galaxies bound to our own local group. The rest will have slipped away, their ancient light faded into the background glow. To them, the universe will seem smaller, quieter, lonelier. They'll have no postcards from across the river, no messages from beyond the canyon. Their cosmic horizon will be much closer. But we're here now. We can still see the far shore. We can still read the stories written in starlight. We can still marvel at the fact that the same physics that hides so much from us also gave us the tools to glimpse it in the first place. And that's the magic of this whole journey. The more we learn about the universe's limits, the more we appreciate the moments when we're lucky enough to peek beyond them. If our cosmic horizon is the edge of what we can see today, then the cosmic microwave background, the CMB, is the earliest message we'll ever receive. It's not just old light, it's the oldest light. A baby picture of the universe taken when it was just 380,000 years old. Now, 380,000 years might sound like a lot, but in cosmic terms, it's practically delivery room footage. If the universe's whole life were a 24-hour day, the CMB snapshot would be taken just after the clock hit midnight, and the first lullabies had started playing. Before this moment, the universe was opaque, not because it was dark, but because it was too bright and too hot. Everything was a thick soup of particles and light bouncing off electrons like a never-ending game of cosmic pinball. Photons couldn't travel freely. They kept scattering, unable to make a straight path anywhere. It was like trying to see across a crowded dance floor at a wedding, where everyone's doing the cha-cha and you're just trying to find the dessert table. But as the universe expanded, it cooled. Eventually, it reached a temperature low enough for electrons to pair up with protons, forming neutral hydrogen atoms. With no free electrons to scatter off, photons could finally move in straight lines. This moment is called recombination, though honestly, it's more like first combination. And just like that, the universe went from foggy to transparent. Light could finally travel freely, and it has been traveling ever since. That's the light we see today as the CMB. Of course, it's not still blazing like it did back then. Over the past 8 billion years, the expansion of the universe has stretched that light from a blinding glow in the visible spectrum to faint microwaves just a few degrees above absolute zero. It's the most subtle kind of souvenir, like getting a postcard where the colors have faded, but the message is still clear. When scientists first detected the CMB in 1964, they weren't even looking for it. Arno Penzias and Robert Wilson were trying to make a radio antenna work properly. They kept picking up this faint, steady hiss, no matter where they pointed it. They thought it was interference, maybe from the city, maybe from cosmic rays, maybe even from pigeons roosting in the antenna. They literally cleaned out bird droppings, thinking it might solve the problem. Spoiler, it didn't. Turns out that hiss was the afterglow of the Big Bang itself, calmly humming across the entire sky. If you could see microwaves, the CMB would be everywhere you looked, no matter the direction it's there, with almost the same temperature, 2.725 Kelvin, across the board, almost. And it's in those tiny, tiny differences, 1 part in 100,000, that we find the seeds of everything we see today. Those tiny fluctuations in temperature and density are the fingerprints of the early universe's structure. Where the CMB was just a hair denser, gravity pulled more strongly, drawing matter together and eventually forming galaxies, stars, and planets. Where it was less dense, vast cosmic voids would later stretch across millions of light years. It's humbling to realize that your existence, my existence, every cup of coffee ever brewed, all trace back to those tiny bumps in a nearly uniform baby picture. The entire tapestry of cosmic history, every star, every black hole, every strange alien world we haven't found yet, started as a little squiggle in the microwave sky. Now, you might wonder, if the CMB is the oldest light, is it also the furthest thing we can see? The answer is yes and no. Yes in terms of light, no in terms of distance. Because remember, space has been expanding this whole time. The light from the CMB started its journey when the universe was a few 100,000 years old, but the place it came from is now about 46 billion light years away. We're not looking at a shell just outside our galaxy. We're looking at the stretched out edge of the visible universe. And here's where things get even more mind-bending. Beyond that shell, the universe keeps going. We just can't see it because any light from further out hasn't had time to reach us yet. Imagine you're standing in a dark forest at night with a flashlight. The trees within your beam are all you can see, but you know the forest continues far beyond the edge of the light. The CMB is the tree line of our cosmic flashlight. The CMB also gives us some of the best evidence for the idea of inflation, that brief, wild growth spurt the universe went through in its first trillionth of a second. Inflation stretched tiny quantum fluctuations into the vast structures we see today, and it explains why the CMB is so uniform in temperature. Without inflation, distant regions of the CMB shouldn't match so closely. They'd never have been in contact to agree on a temperature. Inflation in a cosmic mic drop moment solves the problem. Scientists have mapped the CMB in extraordinary detail using satellites like COBE map and Planck. These maps aren't just pretty, they're treasure troves of data. They let us measure the age of the universe, its composition roughly 5% ordinary matter, 27% dark matter, 68% dark energy, and even its geometry, flat within measurement error. Not bad for something that looks to the untrained eye like rainbow-colored static. And in a way, that's the poetic heart of it. The oldest thing we can see is also one of the quietest. No explosions, no drama, just a calm glow from a time before stars, before planets, before anyone could look up and wonder. It's the universe's origin story, written not in words, but in temperature maps. Every time I think about the CMB, I imagine it as a kind of background music for the cosmos. It's been playing for 13.8 billion years, so faint we can't hear it, but always there. And in that hum, there's a record of everything. The moment the fog lifted, the seeds of all structure, the gentle curve of the universe's future. The next time you're microwaving popcorn, think about this. The same kind of waves heating your snack are also carrying the oldest story in existence. And unlike your popcorn, they'll still be around billions of years from now, long after our little corner of the cosmos has gone quiet. So from our moving, expanding horizon limited viewpoint, the CMB is both a farewell and an introduction, the oldest light we'll ever see, and the first chapter in the book of everything. We've talked about the light we can see from the nearest stars to the farthest whisper of the cosmic microwave background. But here's the twist. Most of the universe isn't made of stuff that gives off light. In fact, most of it doesn't give off anything we can see. Welcome to the shadowy world of dark matter and dark energy, the invisible majority. Let's start with dark matter, the quieter of the two, though no less mysterious. The idea first popped up in the 1930s when Swiss astronomer Fritz Zwicky was studying galaxies in the Coma cluster. He noticed they were moving around each other way too fast for the amount of visible matter holding them together. If the only mass in the cluster came from the stars and gas, we could see the galaxies should have flown apart like marbles tossed onto a table. But they didn't. Something unseen was providing the extra gravity to keep them bound. Fast forward a few decades, and astronomer Vera Rubin made similar observations for individual galaxies. She measured the speeds of stars orbiting their galactic centers and found something surprising. Stars far from the center were moving just as fast as stars near the middle. That's not what should happen if gravity came only from visible matter. The outer stars should be slower, like planets in our solar system. But nope, they were zipping along as if an invisible halo of matter was holding them in place. This unseen glue is what we now call dark matter. We know it's there because of its gravitational effects, but we can't see it directly. It doesn't emit, absorb, or reflect light. It's like the ultimate introvert, quietly shaping the universe while avoiding all direct attention. And dark matter isn't rare. Oh no, it makes up about 27% of the total contents of the universe. Ordinary matter, everything you've ever touched, eaten, or stubbed your toe on, makes up just 5%, the rest. Well, that's the even stranger part. Dark energy. We'll get there in a moment. The thing about dark matter is, we still don't know what it actually is. We've got theories, WIMPs weakly interacting, massive particles, axions, sterile neutrinos, but so far, no smoking gun. Physicists have built huge underground detectors filled with super pure liquids, hoping a dark matter particle will occasionally bump into an atom and leave a trace. So far, these experiments have turned up nothing conclusive, which is either frustrating or thrilling depending on your patience level. If dark matter vanished tomorrow, the universe would be unrecognizable. Galaxies would lose their glue stars, would drift apart, and large-scale cosmic structures would unravel like a badly knitted sweater. We literally live in the web that dark matter built a vast invisible scaffolding on which all the visible parts of the universe hang. Now, if dark matter is the quiet architect of the universe, dark energy is the weird landlord who keeps making the building bigger. We stumbled onto dark energy in the late 1990s when two teams of astronomers were studying distant type Ia supernovae, exploding stars that act like standard candles for measuring distances. They expected to find that the universe's expansion was slowing down under the pull of gravity. Instead, they found the opposite. The expansion was speeding up. It was like tossing an apple into the air and watching it zoom upward faster and faster instead of falling back down. Something was pushing the universe apart, and it wasn't anything we could see. This mysterious push is what we now call dark energy. And here's the kicker. Dark energy isn't just a minor player. It makes up about 68% of the total energy content of the universe. That means almost 7/10 of everything is whatever dark energy is. We don't know if it's a property of space itself, like Einstein's cosmological constant, or something more dynamic like a new field or force. But whatever it is, it's driving the acceleration of the cosmic expansion. Put it all together, and here's the pie chart of reality. 68% dark energy, mysterious expansion fuel, 27% dark matter, invisible gravity glue, 5% ordinary matter, as planets' coffee mugs. In other words, we understand only a tiny fraction of what the universe is made of. The rest is invisible, untouchable, and for now unexplained. It's as if you opened a history book and found that 95% of the pages were blacked out, but you could still piece together the story from the few visible paragraphs. This doesn't mean we're flying blind. The effects of dark matter and dark energy are measurable, even if the causes aren't. We see dark matter's fingerprints in the rotation of galaxies, in the bending of light through gravitational lensing, and in the structure of the cosmic web. We see dark energy's hand in the way galaxies are drifting farther apart faster over time. And there's a strange comfort in knowing that our ignorance has boundaries. We might not know what dark matter is, but we know it's not made of ordinary atoms. We might not understand dark energy, but we know it's consistent with the expansion patterns we observe. The universe might be mysterious, but it's not random. If this makes you feel small, well, good. In cosmic terms, we are small, but we're also rare. We're part of the only 5% of the universe that can look back at itself and wonder where the rest came from. So what does all this mean for our future view of the cosmos? Here's one possibility. As dark energy keeps pushing the universe apart, distant galaxies will continue to slip beyond our cosmic horizon. Eventually, only our local group of galaxies, the Milky Way Andromeda, and a few dozen smaller ones will remain visible. The rest will fade from sight, not because they've gone anywhere dramatic, but because the light they emit will never reach us. In that far future, astronomers might not be able to detect the CMB or see the expansion at all. To them, the universe could look static and small, with no hint of the grand cosmic drama we see today. It's a little like living in a house just as the library next door is closing down forever. We're lucky enough to browse the shelves while they're still open. For now, though, we're in a golden age of cosmology. We can see the baby picture of the universe in the CMB, trace the invisible scaffolding of dark matter, and watch dark energy stretch the stage beneath our feet. We can measure, map, and model, and maybe, most importantly, admit what we don't yet understand. And if you ask me, that's the best part. Not knowing is the fuel for curiosity. It's the reason we keep building better telescopes, sending out new probes, and dreaming up wilder theories. The invisible majority isn't a brick wall. It's an invitation. It's the universe saying, there's more here. Come and find it. After spending so much time talking about the crowded parts of the cosmos, galaxies, clusters, filaments, it's easy to forget that most of the universe is, well, nothing. Or at least nothing we can easily see. Welcome to the cosmic void's enormous, nearly empty regions that make up the bulk of the universe's volume. Imagine you're looking at a 3D map of the universe. The cosmic web we explored in part 14 forms the bright lines and knots. Now everything between those threads, that's void. These aren't just small gaps. We're talking about regions tens to hundreds of millions of light years across, with only a sprinkling of galaxies, sometimes just a handful, drifting in the emptiness. One of the largest we found is the Boötes Void, discovered in 1981. It's about 330 million light years across. If the Milky Way sat in the middle of it, you wouldn't see another galaxy in the night sky without a telescope. No Andromeda, no triangulum, just a black velvet backdrop with maybe one or two faint specks. Astronomers call it a supervoid, which is accurate, but I feel like cosmic no man's land has a nice ring to it. Voids aren't completely empty. There's still dark matter, thin gas, and the occasional lonely galaxy. But compared to the bustling filaments, they're the quiet suburbs of the universe. And just like suburbs on Earth, they can be oddly peaceful or unsettling depending on how you feel about silence. So how do these massive gaps form? In the early universe, matter wasn't spread out perfectly evenly. Some regions had slightly higher density, which meant stronger gravity, which pulled in more matter over time. Those areas became the filaments and clusters. Other regions started slightly underdense. So as the denser regions pulled material toward them, the underdense regions lost even more matter. Over billions of years, the dense got denser and the empty got emptier. It's the cosmic equivalent of the rich get richer. Voids come in different sizes and shapes. Some are nearly spherical, others more irregular, shaped by the surrounding filaments. They're not static either. They slowly grow as matter continues to flow out toward denser regions. In a way, they're like the negative space in a painting. You might focus on the bright strokes, but the emptiness gives the structure its form. Interestingly, living in a void might not be as bad as it sounds. Some studies suggest that galaxies and voids can actually form stars more efficiently thanks to lower gravitational harassment from neighbors. It's like having a farm in the countryside instead of a cramped city apartment. More room to spread out, fewer noisy neighbors, and no one bumping into you at the cosmic grocery store. That said, the void life would be lonely. From a cosmic perspective, we're in a moderately populated region. The Milky Way sits near the edge of the local void, which is about 150 million light years across. We're close enough to filaments and clusters that the night sky is full of galaxies for our telescopes to admire. But had we evolved in the heart of a deep void, our picture of the universe might have been very different. Without nearby galaxies to observe, early astronomers could have concluded that the Milky Way was the entire universe. And that's a theme you'll notice again and again in cosmology, where you shapes what you think is out there. Our vantage point is a kind of cosmic privilege. We just happen to live in a place and time where the universe is rich with visible structures, and the light from distant galaxies still reaches us. Billions of years from now, as expansion continues, many of those galaxies will disappear beyond our horizon. The cosmic web will fade, and the voids will dominate even more. But voids aren't just empty curiosities. They're valuable tools for understanding the universe. Because they're so underdense, they're especially sensitive to the effects of dark energy. The way voids grow over time gives us clues about how fast the universe is expanding and whether that rate is changing. In some theories of modified gravity, voids would evolve differently, so measuring them is a way to test those ideas. We can also use voids as natural laboratories. Light traveling through a void experiences less gravitational lensing than light passing near a cluster, which means we can compare the two paths and learn about the distribution of matter. Voids also tend to have cleaner cosmic microwave background signals with less interference from intervening galaxies and gas. And here's a fun twist. Voids might help explain one of cosmology's current puzzles, the Hubble tension. That's the disagreement between different measurements of the universe's expansion rate. Some researchers have suggested that if we happen to live in a slightly underdense region, not an extreme void, but underdense enough, it could skew local measurements of expansion. It's a controversial idea, but it's one more reminder that the universe's emptiest places might hold important secrets. When you think about it, voids are as much a part of the cosmic design as galaxies are. You can't have structure without emptiness. The web needs its gaps. In fact, the presence and size of voids are predictions of our best cosmological models. If the universe were truly uniform, with no voids, it would be a sign that something fundamental was wrong with our understanding. So the next time you hear the phrase empty space, don't picture nothingness. Picture a region so vast that you could fit hundreds of Milky Ways across it and still barely see a flicker of light. Picture the quiet hum of dark matter and the faint glow of a few solitary galaxies stubbornly shining in the dark. And remember that those dark spaces aren't just gaps, they're the counterbalance that lets the bright parts of the universe stand out. In a way, voids are like pauses in music. They're not the notes, but without them, the song wouldn't have rhythm. Without voids, the universe's grand composition would be a single, overwhelming chord instead of the intricate symphony we see today. So here's to the universe's great empty rooms, the quiet halls between the cosmic cities, the vast deserts between the oases of light. They may not get as much attention as the crowded parts, but they're every bit as important to the story of how we got here and where we might be going. One of the strangest and most wonderful facts about the universe is that when we look out into space, we're also looking back in time. This isn't some poetic metaphor. It's a consequence of the simple fact that light takes time to travel. The moon. You see it as it was about 1.3 seconds ago. The sun 8 minutes in the past. The nearest star system, Alpha Centauri, 4 years ago. Andromeda, our neighboring galaxy. You're looking at light that left when early humans were still figuring out fire. The farther away something is, the older the light we see from it, which means the universe itself has given us a natural time machine. Our telescopes aren't just peering into space, they're flipping through the pages of cosmic history. This time delay effect is why astronomers can study galaxies as they were billions of years ago. By looking deep into the night sky, we can actually observe how the universe has evolved from small, irregular clumps of stars in its youth to the majestic spirals and giant ellipticals we see today. Take the Hubble Ultra Deep Field Image, for example. Astronomers pointed the Hubble Space Telescope at a tiny, seemingly empty patch of sky for over 11 days. What came back was a picture of thousands of galaxies, some so faint that their light had been traveling for over 13 billion years. In other words, we were seeing them as they looked less than a billion years after the Big Bang. And now, with the James Webb Space Telescope, that time machine has gotten even more powerful. JWST's infrared vision can see even farther back into an era when the first galaxies and stars were forming. It's like upgrading from reading your grandparents' photo albums to watching actual footage of them as kids. But it's not just galaxies that act as snapshots of the past. The entire sky is filled with relic light from the early universe, the cosmic microwave background, CMB. This is the faint afterglow of the Big Bang stretched into microwaves by billions of years of cosmic expansion. When we detect it, we're seeing the universe as it was, about 380,000 years old, long before stars, planets, or YouTube channels existed. Think about that for a second. Everything you've ever known, every tree, every ocean, every bad haircut is part of a timeline that fits neatly into the last zero. 0.03% of the universe's history. That's humbling. Also a good reminder that the universe will keep going long after we're gone, probably not even noticing our absence. Harsh but true. The time machine analogy also helps explain why space travel to distant galaxies is tricky. Even if we could move at near light speed, by the time we arrived, millions or billions of years would have passed. The galaxy we set out to reach might not look anything like it did when we first saw it. It might not even exist anymore. Space is patient, we are not. And yet, there's something deeply human about wanting to see more. That's why astronomers push for bigger telescopes and better detectors. Every new advance lets us rewind the cosmic clock just a little further. There's also a subtle twist here. Because of the expansion of the universe, the most distant objects we see now are actually much farther away than they were when they emitted their light. Some of the galaxies whose ancient light we detect are now more than 30 billion light years away, thanks to the stretching of space itself. The light left when they were young and close, but space has been expanding in the meantime, like someone slowly walking away while you're still waving at their old position. This means our cosmic time machine is a little weird compared to, say, a movie rewind button. We can't just go to year one and then move forward in real time. Instead, the farther back we look, the more the very stage we're watching has shifted beneath our feet. There's another layer of complexity. Sometimes massive objects along the way bend light through gravitational lensing, magnifying and distorting distant galaxies. This is like watching an old film through a funhouse mirror, except the mirror is a cluster of galaxies a billion light years away. It's a nuisance if you want a clean image, but it's also a gift. Lensing can bring faint early galaxies into view that would otherwise be too dim to detect. And while looking back in time is scientifically incredible, it's also emotionally powerful. We're seeing light that's been traveling toward us since before Earth formed. Some of those photons have been on the road for billions of years, dodging stars, sliding past black holes, weaving through the cosmic web, just so they can end their journey in the detector of a telescope, in a remote observatory, or maybe even in your own eye as you glance through a backyard telescope. It's hard not to anthropomorphize that light. It's like meeting an old traveler who has seen things you can barely imagine, carrying whispers from an ancient past you can never visit in person. And here's the kicker. The deeper we look, the closer we get to the cosmic dark ages. This was the time after the CMB, but before the first stars lit up, when the universe was filled mostly with neutral hydrogen gas. It was dark, at least to visible light, and astronomers are now working to uncover how that darkness gave way to the brilliant tapestry of galaxies we see today. That transition, called cosmic Ryanization, is one of the big frontiers in astronomy. We know it happened within the first billion years, but the exact timing and process are still under investigation. Was it driven mainly by the first stars, early galaxies, quasars powered by supermassive black holes? Probably some mix of all three, but figuring out the proportions is like piecing together the first chapter of a very long novel when half the pages are missing. So the next time you step outside at night, remember that the stars are not just points of light. They're windows into the past. You're not seeing them as they are. You're seeing them as they were. Every glance at the sky is a history lesson no textbooks required. In that sense, Astronomy isn't just about exploring space, it's about exploring time. It's about realizing that our present moment is one tiny frame in an epic film that began billions of years before we arrived and will continue billions of years after we're gone. And if that thought makes you feel small good, you are small, but you're also in a privileged position, a conscious being in a vast ancient universe with the ability to not just exist in it, but to understand it even if just a little. The universe's time machine is always running, whether we're looking through a telescope or just glancing up during a late night walk. We can't control it, we can't rewind it, but we can appreciate the ride. And maybe that's enough. By now, we've sailed across a lot of night ocean expansion horizons, ancient light, the invisible majority, the cosmic web, the silent grace of voids, and the time machine, hiding in every photon. There's one more idea that keeps tugging on the sleeve of all of this: the way the universe can have limits without ever needing a hard border, or as I like to call it, edges. Without edges, we're used to edges. Lunchboxes, sidewalks, phone screens, pizza slices, they end. You can point at the edge, put a finger over it, drop a crumb off it. So when someone says, maybe space doesn't have an edge, the brain rebels a little. Excuse me. It says everything in my entire life had a perimeter. Where's the rim on this thing? Let's start with a gentler world, one that lives in 2 dimensions. Picture yourself as a tiny explorer who can only walk on the surface of a perfect sphere, a planet with no mountains or oceans, just a smooth, round skin. You can head north, southeast, or west forever, but you can't dig down or fly above. To you, the surface is the entire universe. If you walk straight long enough, you eventually loop back to where you began. You never hit a border, no fence, no cliff, no end of world sign next to a sleepy guard with a clipboard. The world is finite. You can measure its total area, but it has no edge. That's the first trick to hold on to. Finite is not the same as having a boundary. On the spherical surface, finite means measurable, limited in total size, while unbounded means no rim to fall off. Edges aren't required. Now inflate that idea into 3 dimensions, not the sphere's surface, but a full space that curves back on itself. Hard to picture. You're not alone. Our brains didn't evolve to visualize 3-dimensional spaces curving within a higher dimension. That's okay. The essence is simple. You can imagine a universe where every straight line eventually loops. Travel far enough in one direction, and without ever turning, you return home. Finite, unbounded, edge-free. A fan-favorite analogy is the balloon. Draw a bunch of tiny dots on the rubber galaxies and start inflating. As the balloon expands, the dots move away from each other because the surface itself is stretching. No dot is the center. Every dot sees every other dot recede. If you live on the surface, you can walk forever and never encounter a border. The expansion is of the surface, not into the room, because as a 2-dimensional creature, you don't have access to the room. Similarly, when we say our 3-dimensional space expands, we don't need an outside for it to expand into. Space is the stage, not the actor on someone else's stage. Of course, the balloon picture is limited. It tempts you to imagine an outside that our universe is floating in. In real cosmology, space can curve intrinsically. It can be curved by its own rules without sitting inside a larger container. General relativity says mass and energy curve space-time. Space-time tells matter how to move. You don't need an external scaffold to make that geometry real. It's baked into the equations themselves. If spheres aren't your style, try a different topology, the torus, a donut-shaped space. Now, to avoid causing instant vertigo, let's use the simpler, two-dimensional version. Imagine a video game map where walking off the right edge makes you reappear on the left, and stepping off the top drops you in from the bottom. That's a flat torus. There are no hard borders. The edges wrap. From inside, the world feels endless because paths keep continuing, but it's actually finite. You can cover every location with a finite amount of walking, and you'll pass your own footprints if you keep going. In some speculative cosmological models, our universe could have a multiply connected topology like this, where straight lines stitch back on themselves in clever ways. If that were true, and the wraparound scale were small enough, we might even see repeated patterns in the sky, the same distant structures appearing in different directions, like a hall of mirrors that's subtle rather than showy. So why don't we already know the universe's global shape? Because we can only observe a finite patch, our observable universe, bounded by the time light has had to reach us. Within that patch, careful measurements of the cosmic microwave background say space is very close to flat. That doesn't rule out a gentle curvature on scales larger than we can see. Think of standing in a meadow. The ground looks flat as far as your eye can reach, but over an entire planet, you'd eventually notice the curve. We might be stuck in the meadow, mistaking the local for the absolute. Edges also cause philosophical headaches. Suppose there were a literal edge to space a cliff where it all stops. What would be beyond it? More space? Then that's not a true edge, a metaphysical nothing. How do you point to it beyond that? By definition, can't be located or interacted with. The more you try to draw a wall, the more that wall dissolves into a question mark. A finite, unbounded geometry neatly sidesteps that trap. There's no outside, because outside isn't a coordinate the universe supplies. You might be wondering whether the universe's expansion needs an edge. It doesn't. Expansion is a local statement. The distance between unbound points grows with time. In raisin bread language, new raisins aren't being baked into the crust. The dough between existing raisins is rising. No rim, no crust, no beyond, just the distances, changing everywhere at once. Okay, you might say, but what about us? Could we travel in a straight line and return to where we started? In principle, yes, if the universe is closed and the loop length isn't absurdly huge. In practice, it's absurdly huge. The trip would take longer than stars live, longer than galaxies hold their shapes, longer than your snacks will keep, even if you pack the good trail mix with extra chocolate. Also, expansion stretches the path as you go. So while the math may allow a cosmic circumnavigation, the logistics politely laugh. Another subtlety lives in the words we use. Flat, open, and closed refer to geometry, not necessarily to size. A flat universe can be infinite or finite, but wrapped depending on its topology. A closed universe, positive curvature, like a sphere, is finite. An open universe, negative curvature, like a saddle, is infinite. Our best current data point to very nearly flat geometry. On that foundation, the simplest guess is that the universe is also topologically simple. Think infinite plane. But simplicity isn't a law. It's just a good habit. The door to more exotic possibilities is left on the latch. There are even bolder ideas about edges that aren't edges. Some versions of string theory imagine our universe as a three-dimensional brain floating in a higher dimensional bulk. In that picture, Most of the particles and forces we know are stuck to our brain, like sprinkles glued to a donut, while gravity can leak a little into the bigger space. From our point of view, there's still no border we can cross. But to a hypothetical, 5-dimensional tourist with a very fancy passport, our cosmos might look like a sheet with boundaries in a direction we can't experience. That's not established fact. It's an idea on the frontier, but it's a useful reminder that edge is often a question about which dimensions you're allowed to use. Then there's the holographic principle, the notion that the information describing a region of space might be encoded on a boundary of lower dimension the way a hologram stores a 3D image on a 2D film. In some formulations, the true edge that matters isn't a place you can visit, but a surface where information lives. Again, not sci-fi wallpaper, but a serious avenue of research that grew out of trying to understand black holes. If the universe is a book, some of its deepest secrets might be written on the cover. All this talk of topology and higher dimensions can feel delightfully unhelpful when you're just trying to get some sleep. So let's bring it back to something gentler. You don't need to decide tonight whether the universe loops or drifts forever, whether it's flat or saddled or ever so gently curved. What matters is these edges are not required for meaning. The cosmos can be finite and still have no rim. It can be infinite and still feel intimate. It can be centerless and still give every observer a sense of place. And practically speaking, the horizons we face aren't made of stone. They're drawn by time and light. The boundary of what we can know grows as photons arrive like dawn, moving across a field. Even if there's an ultimate limit, even if expansion pulls some stories away faster than we can read them, the pages we do have are more than enough to keep wonder busy. Here's a closing image for your mind to drift with. Imagine a quiet walk at night on a path that gently curves without ever ending. You carry a lantern. Its circle of light moves with you, a little island of visibility floating in a larger dark. The path may loop back on itself. It may wind out forever. You don't have to decide. You just keep walking, and the world keeps appearing edge by edge, right where your light meets it. That's your observable universe. That's your no-edge edge. If there's a lesson in edges without edges, it's this. Sometimes the boundary is not a line you cross, but a way you look. And sometimes the comfort comes not from finishing the map, but from realizing you're already drawn into it. A bright dot on a line that has no end. Pause, ready to keep walking. The path is still there, and the lantern's warm. You've probably noticed that for most of this journey, we've been talking about where the universe is going, how it's shaped, and how we see it. But we haven't really paused to talk about what it's made of. If the cosmos is a cake, and yes, I'm going with cake because we've already used raisin bread and donuts, what are the ingredients? And why, if the recipe is so simple, does the final product end up tasting like, well, everything? Let's start with the obvious layer, normal matter, also called baryonic matter. This is the stuff you meet your favorite mug, and every planet star and interstellar gas cloud you've ever heard of are made from. It's protons, neutrons, and electrons playing together in various combinations. All the elements in the periodic table, all the shiny things in jewelry stores, all the shiny things in the night sky. It's all normal matter. Here's the twist. Normal matter makes up only about 5% of the universe. That's right, the entire Netflix catalog, every cup of coffee you've ever had, the whole internet, every awkward middle school memory you've ever repressed, all of it fits into that 5%. The rest of the universe. Well, that's where the recipe gets weird. Next up is the mysterious dark matter. It doesn't emit light, doesn't absorb light, doesn't even interact with light. It's the strong silent type of the cosmos. We know it's there because we can see its gravitational fingerprints. Galaxies rotate faster than they should if they were held together only by visible matter. Without dark matter, the Milky Way would fly apart like an unwrapped cinnamon roll in zero gravity. Observations of galaxy clusters and gravitational lensing also scream extra mass. Here, dark matter answers that scream. How much of the universe is it? Around 27%, and yet we still don't know what it's made of. It could be WIMPs, weakly interacting, massive particles, or axions, or something we haven't even dreamed up yet. Scientists are running elaborate experiments in underground labs, trying to catch a dark matter particle in the act. So far, crickets. But that just makes the hunt juicier. Then there's the real heavyweight dark energy. It makes up roughly 68% of the universe, and it's even more mysterious than dark matter. It's not just a hidden ingredient. It's an ingredient that's actively changing the recipe as the cake bakes. Dark energy is what's driving the accelerated expansion of the universe. Without it, gravity would have been slowing things down. With it, the cosmic expansion is speeding up like it just got a second wind. We discovered dark energy in the late 1990s by observing distant supernovae. They were dimmer than expected, which meant they were farther away than they should have been if the expansion rate were constant. The only good explanation, something call it dark energy, is pushing space apart faster and faster. It's as if someone not only turned up the oven heat, but also made the cake pan expand mid-bake. So to sum up the cosmic recipe, 5% normal matter, stars, planets, people, coffee. 27% dark matter, invisible scaffolding that holds galaxies together. 68% dark energy, the mysterious force stretching the fabric of space. That's it, 3 ingredients. And yet the result is a universe rich enough to produce Shakespeare black holes, octopuses, and whatever's going on in quantum mechanics. Now here's where it gets even weirder. If you zoom in far enough, normal matter itself is mostly nothing. Atoms are tiny nuclei surrounded by vast regions of empty space where electrons zip around. If you could remove all the empty space from every atom in every person on Earth, the whole human race could fit into a sugar cube, an uncomfortably heavy sugar cube, but still. And yet, despite being a sliver of the cosmic pie chart and mostly empty at that normal matter, is where all the action we care about happens. Dark matter may hold galaxies together, and dark energy may steer the grand expansion, but normal matter is the stage where the interesting stories, life-death tacos play out. One of the great unsolved questions is why the universe has matter at all. Physics says matter and antimatter should have been created in equal amounts in the Big Bang. When matter meets antimatter, they annihilate in a burst of energy. Equal amounts should have wiped each other out completely. But for some reason, there was a tiny surplus of matter, about 1 particle of matter for every billion particles of antimatter. That 1 in a billion advantage is why we exist. The rest is gone converted into pure radiation, and no one knows exactly why the imbalance happened. Somewhere in the early universe, the rules bent just enough to give matter a head start. Another puzzle is how dark matter and dark energy fit into the deeper laws of physics. Are they new particles, new field signs that our understanding of gravity is incomplete. We've built whole experiments, the Large Hadron Collider, the Vera Rubin Observatory, massive underground detectors just to chase them down, and every answer seems to raise more questions. It's also worth noting that while we've known about normal matter for millennia, the concepts of dark matter and dark energy are brand new in cosmic terms. Dark matter entered the conversation in the 1930s, but it didn't become a central focus until the 1970s. Dark energy only crashed the party in the late 1990s. Our cosmic recipe has changed dramatically in just a few human decades, which suggests we might still be missing some ingredients. Maybe the real list looks nothing like the pie chart we love to draw in science talks. If that's unsettling, here's the comforting side. Humans have figured out 95% of the universe is invisible and mysterious. And instead of panicking, we've built billion-dollar machines and spent decades chasing ghostly particles underground. That's optimism, that's curiosity, and it's very on brand for a species that once thought the sky was a solid dome and now sends robots to Mars. So next time you hear someone say, "We're just a tiny speck in the cosmos," you can nod and say, "True, but we're the tiny speck that knows it's a speck and is trying to read the recipe." If the last part was all about the recipe, then this one is about the serving size. Specifically, how do we weigh something as enormous, invisible, and stubbornly uncooperative as the entire universe? You can't exactly put it on a bathroom scale and squint at the number. Even the heavy-duty truck scales at highway rest stops aren't going to cut it. We have to get creative. One of the main tricks astronomers use is gravity itself. Gravity doesn't care if something is shiny or dark, made of protons or pure mystery. It tugs on everything the same way. That means we can weigh the universe by watching how things move. Take galaxies, for example. We can measure how fast stars orbit around the center of a galaxy. If the only mass in the galaxy were the stuff we could see, stars, gas dust, then those outer stars should move slower as they get farther from the center, just like planets in our solar system. But in reality, they whip around at almost constant speed, like they've all agreed to keep the same beat in a cosmic dance-off. The only way to explain that is if there's extra invisible mass holding them in place, dark matter. We can also look at galaxy clusters, the largest gravitationally bound structures in the universe. By measuring the speeds of galaxies within a cluster or the temperature of the hot gas between them, we can estimate the total mass needed to keep them from flying apart. The numbers always come back way higher than what visible matter alone can account for. Dark matter again making itself known without ever showing its face. Another method is gravitational lensing. Massive objects bend space and light follows those curves. If we look at a distant galaxy behind a closer massive object like another galaxy or a cluster, its light will be distorted, magnified, or even split into multiple images. The amount of bending tells us the mass of the lensing object, whether we can see all that mass or not. It's like seeing the universe through a funhouse mirror, except the mirror is telling you exactly how much it weighs. Then there's the cosmic microwave background, CMB, our trusty afterglow from the Big Bang. The tiny ripples in the CMB's temperature and polarization patterns carry a wealth of information about the density and composition of the early universe. By analyzing these patterns, scientists can measure the amount of normal matter, dark matter, and even dark energy like reading a baby picture of the cosmos and figuring out its weight from birth. Speaking of cosmic baby pictures, we can also measure the universe's density by looking at the large-scale structure of galaxies, the way they're arranged in a cosmic web. There's a characteristic scale called the Baryon Acoustic Oscillation BAO imprint, essentially a frozen sound wave from the early universe that acts like a standard ruler. By seeing how this scale shows up in galaxy surveys, we can infer how the universe has expanded over time, and from that, its mass energy budget. All of these methods, galaxy rotation curves, cluster dynamics, gravitational lensing, CMB analysis, large-scale structure, point to the same conclusion. Most of the universe's mass energy is not the stuff we can see. And when different lines of evidence agree so strongly, you know you're onto something real. Of course, real in science doesn't mean fully understood. Weighing the universe is like weighing a sealed box, and realizing most of the weight comes from something you can't see or touch. You know it's in there, but you don't know if it's bowling balls, bricks, or a collection of extremely dense cats. Another fun wrinkle is that the universe's total mass energy isn't just sitting still. Thanks to dark energy, the energy density of empty space itself is playing a starring role in how the cosmos evolves. In the simplest models, dark energy's density stays constant as the universe expands, which means its share of the total mass energy budget grows over time. Billions of years ago, matter both normal and dark dominated. Today, dark energy rules the roost. In the far future, matter will be just a rounding error in the cosmic accounting. And while we can't physically step outside the universe and look at it from above, these weighing techniques are surprisingly precise. The current best estimates from the Planck satellite and other experiments say the universe's density is incredibly close to the critical density, the exact amount needed for space to be geometrically flat. That's like throwing a dart from across the galaxy and hitting the bullseye within the width of a human hair, which leads to one of those philosophical, possibly headache-inducing questions. Why is the universe's density so close to the critical value? This is known as the flatness problem. If the density had been even slightly higher in the early universe, it would have recollapsed by now. Slightly lower, and it would have expanded so fast that galaxies never formed. The fact that it's balanced so perfectly suggests either an incredible cosmic coincidence or some deeper physical mechanism that set it that way. One popular explanation is cosmic inflation, a brief period of exponential expansion in the universe's first tiny fraction of a second. Inflation would have stretched space so much that any curvature got smoothed out, just like blowing up a balloon makes a small patch look flat. It also conveniently explains some other puzzles, like why distant regions of the universe have the same temperature despite never having been in contact before. But inflation raises its own questions, and some physicists are exploring alternatives. Weighing the universe then isn't just about curiosity. It's a way to test our deepest ideas about where it came from, what it's made of, and how it will end. And yes, end is one of those words that makes people sit up straight, so we'll get to that soon enough. For now, just remember, we know the universe's weight without ever lifting it. We've learned its ingredients without ever opening the box. And every new measurement is like adding another decimal place to a number that's been waiting 13.8 billion years for someone to ask. Up until now, we've talked about the universe like a long, ongoing story, a plot in motion, characters developing, mysteries unfolding. But every story has an arc, and ours will too. The question is, what kind of ending are we headed for? Happy, sad, weird. The universe doesn't take requests, but it does leave clues. Right now, all signs point to an ending dominated by dark energy. As we've seen, dark energy makes up about 68% of the universe's total energy budget, and it's making space expand faster and faster. If this keeps up, and there's no sign it won't, galaxies will drift farther apart until eventually the light from distant ones will never reach us. Our cosmic neighborhood will become a lonely island of a few dozen galaxies bound together by gravity, surrounded by an ever-growing darkness. That's the Big Freeze, the most popular ending in the cosmological betting pool. In this scenario, star formation slows as galaxies run out of the cold gas needed to make new stars. Existing stars burn out one by one. The big hot blue stars go first, then the medium ones like our sun, then the slow burning red dwarfs. Eventually, only cold embers remain: white dwarfs, neutron stars, black holes. Over unimaginable timescales, even black holes evaporate via Hawking radiation, leaving behind nothing but a thin haze of low-energy photons. The universe becomes cold dark and effectively dead, a final quiet page in a book that took trillions of years to write. It's a melancholy picture, but don't worry, none of us will be around to send RIP universe cards. This is all trillions of years away. That's trillions with a T, so you've got time to finish your to-do list. Another possibility is the Big Rip, which sounds like a roller coaster, but is actually much less fun. If dark energy's strength increases over time, meaning its density doesn't just stay constant, it actually grows, then the expansion rate will keep accelerating until it overcomes all other forces. First, it'll pull apart galaxy clusters, then individual galaxies, then solar systems, then planets, and finally atoms themselves. In the last fractions of a second, the fabric of space-time will tear apart at every point. That's one way to turn out the lights. On the other end of the spectrum is the Big Crunch. This would happen if dark energy turned out to be temporary, a phase the universe is going through, rather than a permanent feature. If gravity regained the upper hand, expansion would slow stop and reverse. Galaxies would start moving toward each other, merging into bigger and bigger structures. Eventually, the entire universe would collapse back into a hot, dense state, perhaps leading to another Big Bang. Some models even imagine an eternal cycle of expansion and collapse, a cosmic heartbeat. Romantic in a way, if you like your romance measured in eons. There's also the heat death scenario, which is basically a more clinical name for the Big Freeze. In thermodynamic terms, it's the point when the universe reaches maximum entropy, no more gradients of temperature or energy to drive processes. Nothing interesting can happen because everything is equally lukewarm nothingness. If the Big Freeze is the poetic version, heat death is the cold technical memo. And then there are the wild cards, vacuum decay, higher dimensional collision scenarios, pulled from speculative physics that could end everything much sooner and more dramatically. These aren't likely according to our current understanding, but the fact that they can't be ruled out entirely is, let's call it, exciting. Imagine the vacuum of space isn't perfectly stable. A tiny bubble of true vacuum could appear somewhere and expand at the speed of light, rewriting the laws of physics as it goes. We wouldn't see it coming. It's the ultimate plot twist, no foreshadowing, just sudden scene change to nothing. The reality is all of these endings are guesses based on what we can measure today. Our understanding of dark energy is still so incomplete that new discoveries could radically change the forecast. Maybe the universe has surprises planned that we can't even imagine yet, and given its track record, I wouldn't bet against it. Here's the thing, knowing the ending doesn't make the story less worth living. If anything, it makes the present more precious. Stars burn brighter because they're temporary. Moments matter because they don't last forever. And even if the universe ends in a big freeze, trillions of years from now, that still leaves an almost absurd amount of time for life, curiosity, and beauty to play out on the cosmic stage. I sometimes think about it like this. If the universe is a book, we're not even in the last chapter. We're somewhere in the middle, maybe just past a really exciting plot twist, still flipping pages without knowing where the author is taking us. And maybe, just maybe, the act of reading changes the ending. We've already reshaped our little corner of the cosmos by existing in it. Who's to say we can't nudge the story in ways we don't yet understand? As we wrap up this journey, remember, we've traveled from the smallest particles to the edges, without edges, from the birth of time to the far future, from recipes of cosmic cake to weighing the unweighable. And we did it all with nothing more than light math and a stubborn curiosity that refuses to quit. That's the real magic trick here. Not that the universe is vast and mysterious, but that tiny creatures on a small rock can figure out so much about it. So if you've made it all the way to the end of this episode, thank you for walking with me through billions of years and billions of light years. I hope it helped you drift into a calmer place, or at least left you with a little more wonder than you started with. And if you enjoyed our time together in this vast, strange, beautiful cosmos, I'd be honored if you joined me again. You know how it goes. Tap the like button, subscribe. If you haven't already, maybe share this with someone who stares up at the night sky and wonders. Not because algorithms demand it, though. Let's be honest, they kind of do. But because the more of us who are looking up together, the less alone we all feel in this big, expanding dark. Until next time, keep your lantern lit and your curiosity sharper than ever. The path doesn't end here, and neither does the story.